Welcome back, AP Calc AB students. Mr. Record here from Avon High School, and we are going to begin our journey into optimization. Typically, this is one of the last things that are taught in the derivative branch of Calculus 1, and so it's likely that this could be a late semester 1 topic, but depending on what school you're at, it could be an early semester 2, nothing to panic about, as long as we get all the material in before the all-important AP exam. But typically this is, like I said, the capstone of Unit 5. It's one of the last topics of Unit 5, and it's an extension of the things that you've been working on in terms of first derivative tests and second derivative test and function analysis. So let's take a look at what optimization has to say. And in the course and exam description, there's really two topics that are devoted to optimization. 510 is a certain introduction, which I've just basically provided, or I'll read to you here in a second. And in topic 511, we're actually going to get into it. So if I really talk about what is optimization, well, it just simply says one of the most common applications of calculus involves determining what the minimum or maximum value would be of a particular relationship. A company might want to know, what is our greatest profit? What's our least cost? The least amount of time, the greatest amount of voltage, optimal size, least size, greatest strength, greatest distance. So really, before outlining a general problem-solving strategy, why don't we start with a pretty typical example? And that's what we've got right here in example number 1. Let's say that you are a manufacturer and you want to design an open top box that has a square base. And it's got a surface area of 108 square inches for this particular box. What dimension should the box be in order to produce a box with a maximum volume? Let's say that you make little bitty teddy bears and you're going to put these stuffed bears in a box. You would like that box to be fairly large so that you could use fewer of them when you ship, but yet you only have a budget that will basically allow you to purchase cardboard that is of the size 108 square inches. Now you can configure that 108 square inches in a lot of different ways. And I want you to keep in mind that this is an open top box, which might not work real well when you're shipping teddy bears, but we're probably going to use some other kind of a covering for it later on down the road. So we only have to worry about the sides outside of the top. So there it is. That's your typical problem. How do we solve it? Well, you're going to have to come up with a formula. You're going to have to come up with the primary equation. And that primary equation is always going to be linked to what it is that you're trying to find the optimal size for. In this case, you read through the problem and you see the word maximum. So this is obviously a maximization problem. And then shortly after the word maximize, you've got volume. And so that should give you the information that you need. You are going to want to maximize the formula volume equals, well, what is the volume formula? Well, for a box, it's just the multiplication of the 3 dimensions. And as you can see, this box is sort of labeled here just above me. And you can see that the dimensions are x by h. And so that would make a total volume inside the box of x squared times h. Remember, the volume doesn't care whether or not we have a top or an open box, if we have a cover on it or not. Now, here's our dilemma. You've probably gotten to a point in your calculus lives where you know if you want to find the maximum of a particular function, all you need to do is to take the derivative of that function and then go about a few other steps, finding critical numbers and whatnot. The problem is we're not quite in a position to take this derivative. And the reason is because there are too many variables. There are one too many variables in this question. We don't really want to work with the x squared and the h. And the reason is because if we take this derivative with respect to, well, one variable or the other, we're going to have to use implicit differentiation, tack on dx, dx, dh's or dh over dx's, and that's just messy. And so what we need to do is see if we can get rid of one of the two variables. And so in order to do that, we're going to use what I call in my classroom a secondary equation. Sometimes it's referred to as a constraint equation. I really like that word because it suggests that there's some kind of a constraint placed upon these particular relationships here, h and x and whatnot. And so to find this constraint equation, all one must do is find the number that is mentioned in the problem. And it's the only number, 108. And so tie that number back to a concept, and that concept would be surface area. So it's the surface area of the box that would be this 108. Well, what is the surface area of the box that you might ask? Well, that would just be the amount of space that's going to comprise all sides. And you have to think, how many sides does this box have? 5. Remember, there's no top. So we think about the front of the box being a dimension x by h. We use our common sense to realize that there's 2 of those, one in the back and one in the front. And then we do the same thing on these sides that have an x by h. Oh, there's 2 of those as well. I guess those will combine for 4xh in a little bit. And then the bottom of the box is just an x by x square, which is x squared. Remember, there is no top, and so all of this would be equivalent to our 108. And at this point, you can make the decision to solve for one of the 2 variables in your constraint equation. And the beautiful thing is it doesn't matter which one you solve for. I would typically say, let's find the one that's easier to solve for, x or h. And judging by this particular equation, I'm going to say that the h is going to be a little bit easier to come by. And so to make that happen, we're going to do a couple of things. First of all, I'm going to subtract that x squared over to the right, combine my pair of 2xh's to get 4xh, and by the time I divide over 4x, I have myself an equation for h. And you could manipulate this equation if you want to and maybe split it apart and simplify. We might decide to do that in a little bit, but for right now, I'm going to keep that equation as it is. And the reason is because I want to see what my new maximization equation looks like. I want to take that v and I want to figure out if I take x squared, multiply that by the quantity 108 minus x squared over 4x, what does this look like? Well, okay, it's a little ugly, but at least it has the one variable in it that we can so much more work with. All right, so in this particular case, I'm going to call h the bad variable. We got h out only in terms of x. Things are looking good. We can probably do a little simplifying by way of multiplying through this x squared, or how about we cancel a little bit first? The x squared and the x cancel, and we distribute the remaining x in. And I want to say we're going to get something that looks like this. And I think we're well on our way to being able to take a derivative. The derivative would probably be a little bit easier to take if we did just a little bit of simplifying. So the 108 divided by 4, I want to say that that's 27. And then, of course, the x cubed over 4 can be written as 1/4 x cubed, for one way at least. And then I'd say we got a fairly easy function v that we can take the derivative of. So v prime, who are you? Well, you are 27 minus 3/4 x squared, of course. And in typical fashion, in finding a maximum or minimum, we would find critical numbers and go about setting up a number line test so that we can truly pinpoint our max value. And so when does v prime equal 0? Well, that turns out to be whenever this whole thing is equivalent to 0. And so when I set this equal to 0, basically I'm going to be able to add Add 3, yes, add 3/4 x squared over to the right. And then I can take 27, that's equivalent to 3/4 x squared, of course. And then, oh, what am I going to do next? Multiply by 4, which is 108, which is going to be 3x squared. Divide by 3. Boy, it turns out we get very lucky. Not only is 108 divisible by 3, it's divisible, I guess, fairly nicely, right? 3 goes into 108 36 times, but the result is a perfect square. Oh my gosh, who wrote this problem? So when you take the square root of both sides, by definition, x has to be plus or minus 6. Algebraic, the rules that we have to follow. But since this is a geometry question, there's no way that the x can be a negative 6. So only 6 is going to be the value that we're concerned about. Okay? Now, the next thing that we want to do is make a decision here. You guys can either use the first derivative test or the second derivative test to verify. But I want to make sure that 6 truly is a maximum value. And so if you remember back to your second derivative test technique, you can take the second derivative of this particular expression, which is going to be 0, or I can work up here if you want, 0 minus 6/4 x. 6/4 is the same, of course, as negative 3/2. And then if I plug in my critical value from my first derivative into my second derivative, you will learn that you get a negative answer. I think it's negative 9. And because that second derivative is negative, we have ourselves a max. Yay. Now, remember, you could also use the first derivative test. That would involve setting up a number line, testing a value on either side of 6, and coming up with the correct signs that will give you this max. And I'm going to show you that. I'm not going to ever advocate that you have to do both the first and the second derivative test for the same problem because that's kind of silly. But here's what the second derivative, or I'm sorry, the first derivative test might look like. Plug in 5, find out what v prime is going to be, and v prime is going to end up giving, it's a little tricky, it's 27 minus, let's see, who used 5? Who said 5? Let's use 1. 1's going to be a little easier, right? 27 minus 3/4, that's certainly going to be positive. And if we plug in something like, well, maybe we're now going to have another bit uglier number, we could use something kind of safe like 8. We just have to figure out what's 27 minus 3/4 times 8 squared. That's 3/4 times 64, I believe. And if you look at this very carefully, the 64 over 4 would be a 16. 27 minus 3 times 16 is definitely going to be negative, you guys. And so we're going to be all about the negative value to the right of 6 and all about positive v primes to the left. And that's what we want for a maximum. We change from an increasing to a decreasing behavior. And so the only thing left to do is just answer the question. Hey, what would the dimensions of the box be to produce the maximum volume? Well, we've already determined that our x is going to be 6. I've got it circled down here. And so the dimensions would be 6 by 6 at the bottom, but you don't know what the height is yet, right? H. And so I would just suggest that we go to some place that has h, like right here, and figure out what is h when x is 6. And of course, that would be 108 times 6 squared over 4 times 6. And so 108 minus 36. 108 minus 36, what is that? 72? And if you divide that by 24, turns out that you get a nice integer value of 3. Wow, who wrote this problem? It has such great dimensions. And so your final answer is simply the box should be 3, and you want to make sure you get your size, inches, 3 inches by 3, I'm sorry, 3 inches by 6 inches by 6 inches. And just so you know, it doesn't matter what order you write these 3 numbers. You know that 6 occurs twice because there's 2 x's, and the h occurs once. Because all you got to do is just like take the box and rotate it and sit it on a different side, and then the length and the width can be whichever 2 of those numbers you want, and the height would be the third one. So that would take care of the problem. That would give you the maximum volume as long as you had a surface area of 108 square inches, not including the top. And one of the things that's kind of neat about this problem is that if you really think about it, there could be so many different types of boxes that make this true. In other words, you've got 5 boxes right here, and all 5 have something in common. What they have in common is that the surface area of all of these boxes is indeed 108 square inches. I'll let you guys figure that out and verify it on your own, but I do promise that if you multiply all of the lateral 4 sides and the bottom, you would get that 108 particular surface area. But you can see that they each have a very different volume. And the one in this group that happens to have the biggest is number 4 over here, which happens to be the 6 by 6 by 3. And what's beautiful about this method is that it's so, I guess, concrete in the way that you approach it. You don't have to leave anything to chance. You don't have to experiment and try different sizes and measure it. It has the calculus behind it that will certainly back it up. Now, I want to leave you with one last thing here before we take off. I want to take a look at the graph of this just really quickly. All right, here we go. I'm using the TI Inspire calculator, but you could certainly replicate this on a TI-84 or any other model for that matter. So what I've done is I've kind of found my way into a calculator screen here, and I've graphed, or I've entered the original function. If you remember, the function had a base of x by x squared, and we had discovered that the height is 108 minus x squared over 4x. And this is, of course, before we simplified, which you could type it in either in a simplified version or what we have, a non-simplified version. Now, when I hit enter, I'm probably going to be a little maybe disappointed here. I don't know. Am I going to be disappointed? Yeah, it seems like I'm a little disappointed because I don't see anything, right? Well, the reason I don't see anything is because we probably have to change our window just a little bit. And if you recall, our final answer for this particular problem had dimensions of 6 by 6 by 3. And if you actually find the volume 6 times 6 times 3, that is 108. So I likely need to change my window size so that I have a Y maximum that's at least 108. Maybe if I go 120, that's going to be safe enough. If I want to, I could clean up the Y minimum, maybe make it like -10, just so that I can see the x-axis okay. I might want to change my scale to something that's not so kind of annoying. So 10, each block being 10 units. And because I can't really have a negative x, maybe I'll change this to like -1 just so I can see the y-axis with maybe a scale of 1. So maybe this will give me the chance to see something. And you know, I probably don't see something. And why not? Well, it's because I didn't enter the function. It like disappeared on me. It's okay. I think I may have hit delete instead of hitting enter. So it's okay. You guys get to join me live and actually type this in with me. So remember, we have 108 minus, and I believe it was 3x squared, if I'm not mistaken, and then all divided by 4x. Okay, I like to double check that just really quickly. 108, no, it's 108 minus x cubed over 4x. Good thing we checked, huh? So let's fix that and hit enter. Now we're in business. Now we see the graph of this volume. And the really cool thing is we can go in and we could analyze this graph and we could find its maximum and we could verify, did all this calculus that we do make sense? And boom, check it out, guys. The maximum is indeed 108 cubic inches whenever the x was 6. Anyway, I hope this kind of piques your interest of getting a little bit into this wonderful world of optimization, we have lots more videos coming up. Be sure to check them out. Until next time.